My next example is slightly different than our previous two examples, which were polynomials, right? So they're continuous everywhere, and they are very nicely smooth, well-behaved functions. Here we have something which is a piecewise defined function. You can see it's periodic. I don't think I graphed it beautifully, but you get the idea. You can read up the numbers, right? So this is a periodic function. It's got, and this function is continuous, right? I can draw it without lifting my pencil off the paper. The limits at all the points are full limits, not discontinuous, but it's got these corners. So that's something a little bit different when it comes to, let's look at the derivative and let's see what the graph of the derivative looks like. And we can just figure it out totally from the graph, right? So, because I can look at what's going on between -1 and 1, I have a horizontal line. The slope is 0. So between -1 and 1, the value of the derivative is 0. Okay? And in fact, the reason I chose this as an example is because it's all a bunch of lines, right? So we can figure out, for this example, we don't have to kind of guesstimate what the value of the derivative is. We can read it right off of the graph, and we can graph the exact value of the derivative. Okay, so if I'm looking at x between 1 and 2, I've got a line, rise is 2 and run, well, -2 and 1, right? So this here between 1 and 2, this is a line of slope -2. So that gives me that. Whereas over here, from 2 to 3, I've got a line of slope +2. And now this just kind of repeats, right? Here I've got, for the next 2 points, I've got a line slope 1. Slope 0 at 1, 2, 3. And then here I've got -2 again. Looks like I've got +2. And then the same thing over here. This is from -1 to 0. I've got +2. Here I've got 0. So it would be, so here I've got 0, but I forgot that I need to do the -2 part. Yikes. And now we have the 0, right? +2, -2, 0, +2. It's okay. So +2 here. All right. Yeah, I got it straight, right? That looks good. Okay. So this is what my derivative is going to look like. It's piecewise. It's periodic. The same way this one is piecewise and periodic. This one's got a whole bunch of discontinuities. Now you'll notice the other thing I did is I put in the open circles. The reason I put in the open circles is actually what we're going to be discussing throughout the rest of this video. Because honestly, the derivative simply does not exist at these corners. And if you think about why the derivative doesn't exist, you can sort of think about it graphically. How would I tell you what the tangent line is at this corner, right? If I put my tangent line at this corner, it could be anything. It could be all of these different tangent lines. So there's like an infinite possible number of lines that just touch that at one point and no other, right? So I can't pick one specific tangent line because it's not unique. Mathematically, that means the limit doesn't exist. That limit of the derivative now is what I'm talking about. Because remember, the derivative is a limit. So here it is. I left it on the board for this reason, right? we said that this is the value of the derivative if this limit exists. And then we started doing those limits and they all turned out great if we did the algebra right. And we never got back to that important part of the definition, which is if this limit exists. Well, it turns out it doesn't always exist. Here's an example where we can just see by what we're looking at the different slopes, why it doesn't exist at those points. If I'm looking at the slope here, of course, that's right here, right? The line, the slope is 0. And if I'm going here, the slope is -2. So obviously, this is a full-sided limit, but that limit isn't going to exist over here. Okay? So graphically, we can kind of see that whenever there's a corner or a cusp, something like that, and we'll, meaning like it could be something like this. It doesn't have to be a corner like that. It could be like that. It doesn't have to be super sharp. But whenever they're not actually smooth, right? And that smooth actually is a word we use in math. Smooth means differentiable. So it's like if you don't want to say differentiable all the time, you hear mathematicians say smooth curve. That's what they mean. No, none of this, right? No corners. Anyhow, that was a little bit of a digression. What I wanted to do next, though, is show you using this limit and using a specific function, not one as complicated as this one, but is a simpler one. We'll do absolute value of x. But I wanted to show you what I really mean when I say the limit doesn't exist. So graphically, if I look at the absolute value of x, we know what this looks like, right? There it is. So it's x for x positive, and I'm just going to put the 0 in there. So, and negative x for x negative. So, there we have that. And now and you can tell already from what we've discussed that this is going to be the derivative of these is going to be fine, except for at 0, because 0 is where the corner is. Okay? So what I'm going to do, rather than do the general derivative, I'm just going to look at the derivative as 0. Okay? So if I write this up, f primed of 0, then I have f of 0 plus h minus f of 0 over h. Right? So I can read off what f of 0 is, because f of 0 is just 0. But when I put in f of h, I have a problem because it's either going to be plus h or minus h, depending on whether h is coming from the left or the right. So this by itself isn't good enough. Because it is a piecewise function, and because the definition changes at that point, at the point where we're taking, because we're taking h to 0, right? So I need to look at the sided limits. And by the way, there's one like this on your worksheet where you have to look at the derivative at 0 by doing sided limits. So let's look at it. The limit as h goes to 0 from the left of f of h minus f of 0 over h. So if h is going to 0 from the left, it's negative, right? H is negative. Okay? So if h is negative, that puts me over here. So I'm just putting an h in for x because I'm doing 0 plus h, right? But because h is negative, I'm here, so I have minus h. That's just 0. Okay? So this is the limit as h goes to 0 of minus h over h, so this is -1. right? Because the h's cancel. So from the right, it's the same deal, except for the fact that if I'm going from h on h from the right, when I put this into here, h is positive. So what I have here is not minus h at the top, but from the right I have plus h, right? And then I have limit as h goes to 0 of h over h. Again, the h's cancel, so I just have the limit as h goes to 0. I forgot to write the plus. Darn it. Of 1, which is 1. Right? So I didn't write the negative, but it's fine. You guys, you see what's going on. And that's entirely what we would expect from the graph, right? So if I look at this graph, I know that this is just a line of slope 1. And this is just a line of slope -1. So obviously, if I look at the slope going to 0 and ask myself, what's the limit doing? I'm not going to get the same number, right? Because one of them is 1 and one of them is -1. So you can see that, therefore, the full limit doesn't exist. So I can just write that here. Full limit does not exist. If you are doing a problem, unless they ask you to look at it specifically, like I did on that one on the worksheet, if you just can see that there's a cusp or a corner, you can use that. You say the derivative doesn't exist because there's a corner. That's sufficient. Like, you don't have to prove it with the definition of the derivative unless specifically asked.